All right, guys, we're looking at section 7.4 right now. We're going to look at another way to solve a system of equations, and then we're going to look at partial fraction decomposition as we go through it. And so I'll work through a couple of these with you. Kramer's rule is a nice method for solving systems of equations if you're good at finding determinants. Okay, when it comes to these, doing these problems, what I'd like from you guys is to set up the problems. You can use your calculator to actually calculate the determinants of each of these. But what happens when I'm solving for x or y, the bottom or the denominator here is going to be the coefficient matrix. So whatever's in front of x and y, the determinant of that. And then when I find x, the numerator is going to be, you think of the coefficient matrix, except you replace the number out in front of x with the constant. And then when you're looking for y, you replace the number out in front of y with the constant. And I'll go through an example with you here. Okay, so if I want to solve this using Kramer's rule, here's what I'm looking for from you guys, okay? So x equals, you're going to have a determinant over a determinant, okay? On the bottom, it's going to be just the coefficients of what you see up there. So 2, -5, -3, and 4. Okay? And on the top, it would be the same, except I'm going to replace the x's, because I'm solving for x, with the constant. So this one's going to be 9, -5. And the bottom's going to be 10, 4. Okay? And so then, whether you do this by hand or you work it out on your calculator, I have to find the determinant on the top and the bottom. So on the top here, this is 36 minus, I think this is a -10 here. Yeah. So I have 36 minus 50, which is -14. Okay. On the bottom, I have 8 minus 15, which is -7. And so you divide those out, and of course you get 2. So that's going to be your x, okay? Your y, okay? The bottom's the same. I really could have just written -7 on the bottom, but it's that same coefficient matrix, okay? And then the top is going to be the same matrix, except I'm going to replace what's out in front of y with the constant. So it's going to be 2, then 9, and -3, then -10. Okay, so when I work that out, I get -20 minus a -27. So -20 plus 27, which is 7. On the bottom, we said we got -7, so that's -1. And so our solution to that system, x is 2, y is -1. That's our final solution. So what I need from you guys, though, is this setup. You solve those determinants however you want, but I need to see this setup anyway, okay? All right, 3 by 3, it's the same rules. The coefficient matrix goes on the bottom. If I'm solving for x, I replace the x column with the constants. If I'm solving for y, the y column's replaced with the constants, etc. So that's not going to be any different than what we were looking at, okay? I'll just show you how to set it up, okay? So x equals, okay, because I'm solving for x on the top, I'm going to replace the x's with that constant. So it's going to be -1, then -2, then 3. That 1 will go there, so 1, 1, -5, and then 2, 3, 4. Okay, on the bottom, the coefficients. So 1, -2, 3. -2, 1, -5, 3, 3, 4. And then, use your calculator to find the determinants here, guys. You don't have to beat yourself up and do this by hand. Okay, so on the top, the determinant is 12. On the bottom, it's 6. So x has to be 2. Okay? Y. Okay, well, actually, I know what the coefficient on the matrix on the bottom is going to turn out to be 6 because it was here, so I'm just going to do that. I'm going to replace the y column with these, so I'm going to get 1, -1, 3, -2, 1, -5, and 3, 2, 4. okay? And what I get on that one on the top is a 0 on the top and a 6 on the bottom. So of course that's 0, okay? And then z, okay, we know we're gonna get a 6 on the bottom. We're gonna replace the z column with these constants. So 1, negative 2, negative 1, negative 2, 1, 1, and 3, 3, 2. And when you go into your calculator and you find the determinant of that, you get a negative 6 over a 6, which is a negative 1. So your solution then, x was 2, y was 0, z was negative 1. Okay? So that's what I'm looking for that. Set it up, use the calculator to help you solve. Okay? All right, now we're going to switch gears a little bit to partial fraction decomposition. This page just takes you through what we need to do. If we have a rational expression where you've got a polynomial over polynomial, in order to break this down into partial fractions, you have to factor the bottom completely. For the linear factors, so x plus 4, 2x minus 9, whatever, it has to have an x to the first. Each distinct factor and each power of a repeated factor must appear in the decomposition template with a constant numerator. And I'll explain that as we go. And if it's an irreducible quadratic, then you're going to need a linear factor, so like an ax plus b. And I'll work this out with you as we go. So the first couple, we're not going to actually completely decompose these. We're just going to set up the template. Okay? So step 1, we have to factor the bottom. Okay? So I need a 2x and an x. Okay, I need a 3 and a 1. So it factors like that. Each of those factors is linear. And for each linear factor, I need a variable for the numerator. Okay, so for the 2x plus 3, I've got an a. And for the x minus 1, we'll call it b, or x plus 1. And so that's all I need. That's the template for that one, and that's supposed to equal that original. And I'll show you when we get to the point where we're decomposing those, how to do it, okay? For this one, the bottom factor is 2x minus 3 quantity squared. Well, it says on the previous page, let's go back here, each distinct factor and each power of a repeated factor must appear in the decomposition template, okay? Well, that's important. This one has a power of 2, which means I need 2 different fractions. So I'm going to need a over x minus 3 to the first and b over x minus 3 to the second. If that was x minus 3 to the fifth, I would need a c over x minus 3 to the third, and a d over x minus 3 to the fourth, and an e over x minus 3 to the fifth. Thankfully, it was only to the second power, so I could stop there. So that's your template, you guys. That's all I need for that problem. That's all they're looking for, okay? Similar question, give us a template, okay? Well, I got a factor over here, so I can take an x out of everything. That gives me x squared minus 2x plus 1, okay? And that factors 2x minus 1 quantity squared. All right, so I need a numerator for that factor, x, so I need an a over the x. And then I have x minus 1 quantity squared, so I'm going to need something for x minus 1 and something for x minus 1 squared. So I'll need a b over x minus 1, and I'll need a c over x minus 1 squared. That's going to be your template for that one. Okay? Example 5, a couple more templates here. This doesn't factor. There's no numbers that multiply to 3 and add up to 1, so they've factored it for us. Okay? The linear factor is easy enough. They just said they needed a variable in the numerator for that. But if you remember a couple slides ago, if it's an irreducible quadratic, you need a linear numerator. So something x plus something. So because that's quadratic and irreducible, I need bx plus c then over x squared plus x plus 3. Okay, that's going to be the template for that. For part B, you've got a couple of things going on here, you guys. That x squared plus 3 is irreducible, so I've got a quadratic, which means, you know, something x plus something. But it's to the third power, which means I need 3 different ones. One to the first, one to the second, one to the third. So for the first power, I'm going to have an ax plus b, and then over x squared plus 3. And then a cx plus d over x squared plus 3 quantity squared. And because I'm to the third power, I need to go one more. I need an ex plus f over x squared plus 3 to the third power. And all they're asking for is the template here, so I'm good. That's all I need to write, okay? Eventually we'll get to the point where we're solving some of these and we'll have a little bit more algebra, but for now, that's all I need to do, you guys. Okay, now they want us to decompose this, so we're gonna go ahead and do this. This factors to x plus 2 and x plus 5. So I would say a linear for the x plus 2, so I need an a over x plus 2. I need a b for the x plus 5. And that's supposed to equal this 4x plus 11 over x squared plus 7x plus 10. Okay, now, if I'm gonna make this happen, if I were to actually add the left side together, I'd need a common denominator, right? So in doing so, that would be the product of these two denominators. So I would need to multiply a by x plus 5, and b would need to be multiplied by x plus 2 to get my new numerator. Well, and that's supposed to equal that other numerator, 4x plus 1. So that's ultimately what we're doing to solve these, okay? Well, there's an easy way to do this, and then when it gets a little more complicated, there's a matrix way of doing this. We're going to do it the easy way first here. So if I choose an appropriate x value, I can make my life pretty easy. So like if I let x equal -5, then I go through this whole equation here. -5 plus 5 is 0, so that whole expression is gone, okay? -5 plus 2 is -3 times that b, so I'll get -3b. And 4 times -5, where am I here? Yeah, 4 times -5 is, oh, it's 4x plus 11. There we go. -20 plus 11 is -9. Divide, and I know b equals 3. Okay, good enough. And then if I let x be -2, I'm going to get a similar situation, because right here, -2 plus 2 is 0, so I'm going to lose that term. -2 plus 5 is 3, so I'm going to get 3a. -8 plus 11 is 3. This means a equals 1. Okay? Well, what does all that mean? Go back to your original. A is going to be 1. Okay? So I've got... wait a second. Give me 1 second here. Yeah, no, we're good. So a is going to be 1, so we're going to go 1 over x plus 2, and b is 3 plus 3 over x plus 5. And that's what your solution is going to look like. That's decomposed. The sum of those two fractions is equivalent to that original one. Okay? That's the process. Okay? Let's look at another one. If I factor this bottom, this part here, so I have an x plus 5, and then this factors to x plus 2, x plus 5, which is equivalent to, I've got two x plus 5s here. So I've got an x plus 2 and an x plus 5 quantity squared. Okay? Thankfully, they're all linear. Okay, so I need an a over the x plus 2. I need a b over an x plus 5. And because it's quantity squared, you guys, I need c over x plus 5 quantity squared according to those directions. And that's going to equal that original expression. Okay? So when I try to get a common denominator, which is this one here, this a is missing the x plus 5 quantity squared. And the b is missing an x plus 2 and one of the x plus 5s. And the c is just missing the x plus 2. So that's kind of what I've got there. And that should equal that numerator of 9. Okay? And so then, you know, let's let x be negative 5. That'll make this whole term 0. That'll make this whole term 0. Negative 5 plus 2 is negative 3c equals 9. So c equals negative 3. Okay? Let's let x equal negative 2. That makes this one 0 and this one 0. Negative 2 plus 5 is 3. Squared is 9. So I get 9a equals 9. So a is 1. Now, the tricky part on this one is, how do I find b? Right? I can't pick some convenient value and eliminate everything completely. So what I have to do at this point is just pick any value I want for x. I pick something like 1 because it's really easy to put in. But I already know c and a. I know what they equal. So when I let x equals 1, I get 1 plus 5, which is 6, squared is 36, times a, which is 1. So that's just going to give me 36. Okay? Over here, 1 plus 2 is 3, 1 plus 5 is 6, 6 times 3 is 18, and then I don't know what b is, so I've got 18b. Okay? Over here, 1 plus 2 is 3 times c, which is negative 3, is a minus 9, and that's all supposed to equal 9. Okay? 36 minus 9 is 27, so I subtract 27, and I get, okay, so I had 27. 9 minus 27 is negative 18. So I have 18b equals negative 18. b equals negative 1. Okay? So then let me come up here and write my answer. A, we said was 1. So 1 over x plus 2. B, we said was negative 1. So minus 1. And then over x plus 2 and x plus 5. And then c, we said was negative 3, and that was over x plus 5 quantity squared. Okay? That's what your ultimate solution is going to look like for that one. Okay? All right, let's move on here. It's one a little bit trickier. So I go ahead and I got to factor the bottom. So I'm going to group because I have 4 terms. So I take an x squared out of these first 2, and I'm left with x minus 3. I take a 4 out of this next one, and I'm left with x minus 3. So they both have an x minus 3 and an x squared plus 4 left over, which is that quadratic that's not reducible. Okay? That's my common denominator. So that linear term, I'm going to need an a over that x minus 3. But because this one's quadratic, I need that something x plus something. So I need bx plus c over x squared plus 4. And that's supposed to equal that numerator over there. Okay? Ultimately, I'll just leave the equal sign out. So when I get my common denominator, a has to be multiplied by x squared plus 4. And bx plus c has to be multiplied by x minus 3. And that's supposed to equal 3x squared minus x minus 11. Okay, so now I can't do this by picking a convenient value for x. I mean, I could pick 3 maybe and I could solve for a, but we're going to use matrices for this one. Okay, and I'm going to show you how to do this. So I'm going to distribute. This is going to give me ax squared plus 4a. Okay, bx times x is bx squared. Bx times negative 3 is minus 3bx plus cx minus 3c. Okay. All right, so I'm there. Now what I have to do is set up a system of equations that combines the like terms basically. So if I look on the left side, which terms have an x squared? These two. Okay, and on the right side, I have this 3x. So I know that my a plus my b are gonna represent the coefficient of the x squared terms. That has to equal 3. Okay? And then I keep going. My x term, I've got that has x to the first, that has x to the first, and that has x to the first. So that is a negative 3b plus c has to equal negative 1. Okay? Then I look at my constants. I've got a 4a here and a negative 3c here, and that's supposed to equal negative 11. So 4a minus 3c equals negative 11. And I'll tell you what I did at this point. I completely used my calculator. So I went into the matrix menu above x to the negative 1 and went over to math, and I chose RREF, reduced row echelon form. And in the first row, remember I need an A, B, and a C. So I put 1, 1, 0. So RREF 1, 1, 0, 3. And in the second row, there wasn't an A term, but then negative 3, 1, and that negative 1. And then a 4, a 0, a negative 3, and a negative 11. And it spit out my solutions, okay? It said, and I'm gonna kind of move up to here again, it said that A was 1, B was 2, and C was 5. And so what does my solution look like for that? Okay? We said that A was over x minus 3, so that's 1 over x minus 3. And then plus bx plus c, well that's going to be 2x plus 5 over that x squared plus 4. Okay? That's probably the trickiest one we're going to have to do, so you can certainly study that a little bit. Ask me for help, email me, Google Meet, show up to the office hours. Happy to help you guys out in whatever way we can. Okay? And then the last example is going to be pretty straightforward. So in general, if I give you the coordinates of the vertices of a triangle and I want you to find the area of that triangle, I can create a matrix where x1, y1, those are the coordinates of one of the vertices, and then a 1 in that last column, and I do the same thing with x2 and x3. If I take half of the absolute value of that determinant, I get the area. Okay? So this is what we're looking at here. 1/2. The first order pair is 3, 1. And then I always need a 1 in the last column. The second order pair is negative 2, 3. 1 in the last column. The third order pair is 1, 7. 1 in the last column. And then just use your calculator, you guys. I went in and found the determinant to that matrix, which was negative 26, but the absolute value of that is 26. And of course, half of 26 is 13. And whatever our units happen to be on that grid, that's going to be the area, 13 square units. Okay? Last section in college algebra, you guys. Good job for hanging in there. This one, I don't think we're even going to run into any problems in the homework. You can look at it in the book if you need. But there's your assignment, 15 to 45, the odds. So about 15 problems or so to do there. So good luck, you guys.